In order to discuss Newton's laws of motion, we need to introduce the concept of dynamics. When we study the motion of a body in kinematics, we have no concern about the effects of other bodies on its motion. We also neglect any physical property of the traveling body, which can be relevant to its motion. It is not the case in dynamics, where we examine the effects of other bodies on the motion of the body under study, and we also take into account those properties of the body which could be relevant to its motion. In our everyday activity we can determine which objects are in some way related to the motion of a given body. For example, if we throw a ball, then our hand is the body moving the ball which is related to its motion. If the ball is already flying in the air, then the earth and the air itself have some effects on the motion of the ball. Without the effects of these bodies, the motion of the ball was different. In some cases we can eliminate or ignore the effect of other bodies. When we study a free-falling heavy body we can neglect the air resistance, or we can eliminate the effect of the earth for bodies moving on horizontal flat surfaces, such as a table or the floor. In the experiments with bodies moving on flat horizontal surfaces we always observe the same result. If a ball is pushed on the floor or hockey disc is hit on the ice, then it attains a given speed and moves along a straight line on the given surface. We can also observe that the smoother the surface is on which the body moves, the longer the distance it can cover during its motion. Therefore, the smoother the surface is on which the body moves, the smaller the rate of the decrease in its speed is during the motion. We can conclude that the friction between the body and the surface has an effect on the motion of the body, opposing its motion. As a result, the moving body slows down while traveling along a straight line. We can also assume if we could eliminate the friction, then the body kept its initial speed. We can draw the same conclusion if we study the motion of a horizontally launched projectile. Here we can see a cannon shooting a projectile in the horizontal direction. The projectile moves along a parabola, which we explain by the composition of uniform linear motion and free fall. That is, the projectile moved along a horizontal line determined by the direction and the magnitude of the initial velocity gained at the launch. However, there is a contribution of free fall, which is the effect of the Earth's presence on the motion of the projectile. As a result, the vector sum of the initial velocity and the velocity gained from free fall gives the instantaneous velocity of the projectile, which is the tangent to the parabolic trajectory of the moving body. We can assume if we could switch off the effect of Earth's presence, then the projectile had only the initial velocity in the horizontal direction and moved along a straight line. In fact, this condition holds in the space far from any star or planet. Based on these findings we can state the following axiom, which is called Newton's first law of motion. Every body continues in its state of rest or of uniform motion in a straight line, unless it is compelled to change that state of motion by the effects of other bodies impressed upon it. According to the first law of motion, if a ball is rolling on the floor and the effect due to the friction is negligible, then it travels along a straight line at a constant speed. If the ball collides elastically with another ball, then the later one has an effect on its motion. As a result, the moving ball changes the direction of its motion. At the same time, the moving ball resists the effect attempting to change the state of its motion. We attribute this behavior to a property of bodies, called inertia. Inertia of bodies expresses the fact that they remain in the same state of motion without any external effect, and resist any effect attempting to change this state. There are numerous examples for the manifestation of inertia. We can demonstrate the inertia of the glass of water put on a sheet of paper. If the sheet is pulled quickly then the glass will not move. Inertia keeps the glass of water in place because friction between the paper and the glass is not enough to cause the sheet to pull the glass of water with it. Inertia also affects passengers in a car because they are in motion with the vehicle. If a car comes to a sudden stop, the passenger's body tends to keep moving forward until stopped by the seat belt. When the car starts moving again the passenger's body tends to stay in rest and is pushed against the seat. Let us see what the consequences of the first law of motion are. The uniform motion along a straight line or the rectilinear uniform motion is the simplest form of motion, not only in kinematics, but also in dynamics. This is the form of the motion, where the velocity of the body is constant, which does not need external effects due to other bodies to maintain itself. The state of rest can be considered as a special case, where the speed of the body is zero. The view, that the state of rest is the most natural state of the object in nature, as opposed to the uniform linear motion, prevailed science from Aristotelian physics till Galileo's era. This demonstrates that Newton's first law is not an obvious statement. We also have to keep in mind that the first law of motion is the extrapolation of countless results of experiments observed in nature to the ideal limiting case, where a body is completely free from effects of other objects. This statement is an axiom, that is, the first law cannot be proven with direct experiments, since no material object can be withdrawn from the effects of other bodies. If a body has a uniform linear motion or it is at rest, it does not necessarily mean that other bodies do not have effect on it, but different effects could produce a zero net effect by cancelling each other. Here we can see a ball rolling with a constant speed on the floor. The effect of the earth on the ball is compensated by the effect of the floor. As a result, the ball is not free falling but rolling on the floor, and it keeps its initial velocity provided the friction between the ball and the floor is negligible. As seen before, the state of rest can be considered as a special case of the linear uniform motion, where the speed is zero. In our everyday environment, the majority of the object are in rest, as in the figure showing some books placed on the table. Here the effect of the earth on the books and the effect of the table cancel out each other and the books remain in the state of rest. We have seen that Newton's first law of motion describes the motion with respect to a frame of reference. However, the first law of motion does not tell us what frame of reference is used to describe the state of rest or the motion of a given body. It is an important question, since the description of the motion can be completely different with respect to different frames of reference. For example, a body can be in the state of rest with respect to the earth, but it has an accelerating motion with respect to a train traveling on a round track. In Newton's view, the motion can always be described in an absolute space, which is similar, immovable, and without relation to any external body or object. His view was proved to be incorrect in the light of modern physics. Nevertheless, in classical mechanics we can assume that there exists a frame of reference, called inertial frame, in which the first law of motion together with other laws of mechanics are valid. We consider a coordinate system fixed to the lab frame or the Earth such an inertial frame, at least approximately.